Yeah, I think it has started. And let's go back to the slides. So this we have done, and in the break we proved that as a corollary to this, H omega is an integral domain, and we saw two different proofs, one supplied by Aryaman and the one supplied by all of you together. Okay. So now let's come back to singularities. So singularity means what? Singularity means a point where maybe f is not defined, or even if f is defined, it's not holomorphic around that point. So we will say that we will give a definition of isolated singularity in one go. We will say that f has an isolated singularity at a point A if there is a small disk around A such that f is holomorphic everywhere except at A. Okay, so it may be something like 1 by z at 0, where it's not even defined. So that will fit into this. Or it could be somewhere where it's defined but still holomorphicity fails. That also can happen. So an isolated singularity just means in a deleted neighborhood, of that point, f is holomorphic. So there's a deleted neighborhood where f is holomorphic, then that's called isolated singularity. Now the first, so I told you, right, it will come in three flavors, removable singularity, Paul, essential singularity. Let's talk about removable singularity first. So removable meaning what? It can be removed, the singularity can be removed. How will you remove the singularity? By trying to redefine. So it's possible that sometimes you can redefine f in such a way that the extended function is holomorphic. So suppose you take 1 by z. Of course, 0 is an isolated singularity because in a neighborhood of 0, everywhere else it's holomorphic 1 by z. Now the question is it removable or not? The idea is, can you define at 0 some value so that it is holomorphic? And in this example, you can check that you cannot do that. So it's not removable. Okay, so a standard example of removable singularity will be something like sin z by z, which is not defined at 0, right? But at 0, you can define it to be the limit of sin z by z as z goes to 0, which I can guess 1. Yeah, so if you define the number to be 1 there, then you have removed the singularity. So this is the notion of removable singularity. You can redefine the function in such a way that the extended function is holomorphic in a neighborhood of A. You say that the singularity is removable. Now suppose A is an isolated singularity for f, and let D be a small disk such that in D minus A, f is given to be holomorphic. Now suppose f is bounded in some deleted neighborhood. Deleted neighborhood means this, D prime AR, this prime is for deletion, deleting, so deleted neighborhood. D prime AR is all z such that mod z minus A is strictly less than R. That's like the open disk, but it's also strictly bigger than 0. That means z is not equal to A. A is deleted. So suppose f is given to be bounded in some deleted neighborhood. Then I want to say that the point A is a removable singularity. Okay, so under this assumption, you want to say that f is the singularity is a removable singularity. So how does one go about that? What you do is, it's a small trick. You define this function h of z. In D minus A, you know that f is holomorphic, and there you define it as z minus A whole square times fz, and at z equal to A, you define it to be 0. Okay, you consider this function hz. Now what can you say about hz? You can see that this is a differentiable function. Of course, everywhere other than A, of course it is differentiable because both these are differentiable. At 0 also you can check differentiability. That's why I put the 2 here to make sure that it is differentiable. How will you check the differentiability? From first principles. You take, so what is h prime A? Limit z going to A, hz minus ha by z minus A. So hz minus ha will be, what is h of A? H of A is 0 by the very construction. So hz minus h of A is hz itself divided by z minus A. So that is z minus A times fz. And what is limit z going to A of z minus A times fz? It is 0. Why? because limit z going to a of z minus a is 0 and limit z going to a of fz is some finite quantity because of this boundedness assumption. Because of this boundedness assumption, this the limit in order to calculate this turns out to be 0. It will be limit z going to a of z minus a times fz. Fz is bounded near a and therefore the limit is 0. So h prime a is 0. In particular, h is differentiable at a also and h is differentiable everywhere else. So h is differentiable throughout B. Okay, you have seen that h is differentiable throughout B and therefore it has a power series representation on DAR, right? Holomorphic functions you can represent by power series. So h has a power series expansion Cn z minus a, typo here, I should correct it. Cn z minus a power n. This is n. Okay, but it's starting from 2. Why? Because C0 and C1 are 0. Why is that? Because h of 0 is 0 and h prime is also 0. H of a is 0, h of a is 0 and h prime a is also 0. So only from h double prime a by 2 factorial onwards it will be there. So it starts from n equal to 2. C2 also may be 0, we don't know, but what we know for sure is C0 is 0, C1 is 0. Okay, so you have this. Now you define Fa to be C2, this term, the first term. And then Fz is, this Fz is nothing but this power series, Cn plus 2 z minus a power n, and this power series is throughout DAR. Okay, so you have got a power series expansion throughout DAR for Fz, and therefore F is holomorphic. So you have redefined F at A to be this, right? Earlier F was not defined. Now you are defining F at A precisely this number so that F has become holomorphic. In sin z by z, this is what happens. It will be the limit, right? It will be the limit of z going to A of f of z. And that will be C2. And in that example, it will be 1. So you can redefine like that. You can remove the singularity. So if f is bounded in some deleted neighborhood of the singularity, then it is a removable singularity. Okay, now let's quickly do the classification. We will stop there and continue in the next class. So as I said, classification is removable, Paul, essential. Okay, so classification. If you can redefine f at A such that the extended function is holomorphic in a neighborhood, then it is removable singularity. Sometimes, you know, they may exist finitely many complex numbers, C1, C2, etc., Cm non-zero, such that you can subtract this part from fz minus summation k going from 1 to m. This is not like power series, it is like reciprocal of that, ck by z minus a power k, k going from 1 to m. It's a finite quantity. This is what is called the principal part in the Laurent series expansion when we do Laurent series. So fz minus summation k going from 1 to m ck by z minus a power k. Suppose there are finitely many complex numbers ci such that you can do this, and this becomes holomorphic. In other words, this has a removable singularity at A. If that happens, if your singularity A has the property that you can find finitely many complex numbers so that when you subtract this out, the singularity at A becomes removable for this new function, then you say that it's a pole. Okay? This is the definition of a pole. And the third possibility is you take any disk, any open disk around A, and you take the image of that open disk under your function that is dense in C. If you take any small disk, any open disk containing A, and if you take the image of that, then that is dense in the whole of C. Given any point in C, you can find a point near A. You have a sequence in D prime AR, deleted neighborhood of A, such that that sequence f of Zn converges to this point in C. It's dense in C. In this case, you call it essential singularity. Okay, so essential singularities have this property that near essential singularities, you can form a sequence such that f of Zn converges to any point that you give me in C. Any complex number can be approximated by images of f of from a neighborhood of the essential singularity. So this is the classification. So there's a theorem lying here, underlying here, which is that these are the only possibilities, right? Whenever we say that these are all, you have to give a proof. So we are going to prove that. Let's prove this. That if you have an isolated singularity, it has to be one of these three types. Okay, so what we are going to show is, suppose you have an essential singularity and suppose this condition is not satisfied. Suppose it is, suppose you take an isolated singularity and assume it is not essential. So this condition is not satisfied, then you are going to show that it's either removable or a pole, hence proving this result. That's what we are going to do. So suppose the singularity is not essential. Again, what is essential? Any deleted neighborhood of that point, its image under F is dense in C. So if it is not essential, then there is a deleted neighborhood whose image is not dense in C, right? There is a deleted neighborhood, there exists R such that f of d prime AR is not dense in C. So in other words, this is not dense in C. So dense meaning given any point and take any neighborhood that contains points from this set. So it is not dense. So that means there exists a W in C and also a positive number delta such that mod Fz minus W is bigger than delta in D prime AR, right? You are contradicting density. Density would mean given any point W, there is a neighborhood, and given any small neighborhood of W that contains points from D prime AR, f of D prime AR. And you are saying that is not true. So there is at least one W and at least one neighborhood which will not contain points from D prime AR. So there is a W and a delta and an R such that f of z minus W modulus is bigger than delta in D prime AR, by assuming that the singularity is not essential. Now you consider this function, the reciprocal of this, gz equal to 1 by fz minus w. This is well defined, no? Because fz minus w cannot be 0, because fz minus w is bigger than delta. Modulus of fz minus w is bigger than delta throughout this deleted neighborhood. Therefore, this definition makes sense on this deleted neighborhood. For any z in d prime AR, you can define gz to be 1 by fz minus w. Note that G is holomorphic and bounded on D prime AR. Why is that? G is holomorphic because in this deleted neighborhood, F is holomorphic, W is a constant, so that's holomorphic, and that makes sense. 1 by that makes sense, therefore 1 by holomorphic is holomorphic. So G is holomorphic. G is also bounded on this deleted neighborhood because what is G? Modulus of G is modulus of this, which is less than 1 by delta from this condition. It's less than 1 by delta, so it is holomorphic. It's also bounded on D prime AR. Does this remind you of something? If on a deleted neighborhood, if you are getting boundedness, then what can you say? This is what we discussed at the starting of singularities. If you have a function f which is holomorphic on a deleted neighborhood, and if it is bounded on that deleted neighborhood, then what kind of a singularity is that point A? Someone wants to.
It is a removable singularity.
Singularity. Therefore, G has a removable singularity at A, and therefore G extends to a holomorphic function. You remove it. Extends to a holomorphic function in DAR. Now it is not a deleted neighborhood. Throughout the neighborhood, it is holomorphic. Okay, this is by that boundedness criterion for removable singularity. So if GA is not 0, then, right, so G can be extended. So there are two possibilities, either GA is 0 or GA is not 0. You have already extended it. So G makes sense at A. Either GA is 0 or GA is not 0. If GA is not 0, then what is FZ? FZ will be FZ minus W is 1 by GZ, and FZ will be W plus 1 by GZ, and GA is not 0, so even at A that makes sense. So if GA is not 0, then FZ equal to W plus 1 by GZ makes sense in some deleted neighborhood of A. And why is this bounded? Why is this bounded? Because what do you know about G? G is holomorphic and bounded in on D prime AR, and therefore G extends to a holomorphic function. And
I mean, since this is some neighborhood of A, we can
yeah,
take something compact first inside.
correct. Yeah, absolutely. So GA is not zero, right? GA is not zero. So in some neighborhood of A, G is not zero. And you consider 1 by G set, so that will be bounded. In some deleted neighborhood of A, it will be bounded, right? And therefore F is bounded in some deleted neighborhood of A, and
Why are
therefore
we? Why do we need the deletion?
we don't need deleted because GA is not zero, so GA is some constant value. I put deleted because I was appealing to that boundedness in a deleted neighborhood result. You don't need deleted neighborhood. You know that G is bounded in a neighborhood of A, and by that result, on boundedness in some deleted neighborhood, F has a removable singularity at A.
Okay.
Right? Because you don't know about F was not defined at A, no. So still you know the word is singularity, right? Because
Oh,
we are
okay. Yeah. Yeah.
singularity of it. For that reason, you're right. I mean, in a neighborhood of A, it is bounded, but not quite in the sense F was not given to me at A. Therefore, I am continuing to use the word deleted.
Yeah.
Okay.
We can't write the equality for
I'll
it.
write f of a, that's all. I mean, f of a you can define as w plus 1 by g of a and then write, but not otherwise. So, doesn't matter. That's a small minor point. Either way, you can justify by interpreting it correctly. And but anyway, the point is f has a removable singularity at a, and what are we trying to show? If it's not essential, you want to say that it's either removable or a pole. So if GA is not zero, you have shown that it's a removable singularity. In the other case, you are going to show that it's a pole. So if G has a zero at A, then you can ask the question of what order. We have shown in the previous proof, no? If there is a zero, it will come with some finite order. Right? They cannot be a zero of infinite order, no? Because you must have seen that if it's a non-zero function, not identically zero function, then in the power series there is a CM which is non-zero. So up to that only you can pull it out. So there's always a finite order. Any zero comes with a finite order, something that we have already seen in our proof when we were showing zeros are isolated. So it comes with a finite order. Let's say m greater than or equal to 1, and we can pull it over, pull it outside. G of z equal to z minus a power m times g1z for z in DAR, right? Where g1 is holomorphic and g1a is not zero. Both are okay, no? G has a zero at A and it has a finite order. So if you pull it outside, the remaining part is holomorphic, is something that we have already seen. You can take it out and you will get the holomorphic part. This was from the power series, you are taking it out, so the remaining part will be another power series. So that is holomorphic, and G1a not equal to 0 for the same reason, right? Because it is of order m. So if G1a equal to 0, the order would have been more than m. So because the order is m, G1 is non-zero at A. And G1 has no 0 on the deleted neighborhood anyway. Why is that? That is because zeros are isolated, right? G has a 0 at A and G is holomorphic. Therefore, A has to be isolated, 0. And therefore, in this neighborhood, there is no other 0. G1
Wouldn't
has
we
no
have
0.
to go on a possibly smaller neighborhood, or will this
That,
work?
yeah, that's correct. So we can write, so if you write like this, uh, if you write like this, then we know that G1 of A is not 0. and G1 is introduced only here. So you know that there is a neighborhood of A on which G1 is non-zero. That's all that you know. You are right. And let's see. Yeah, let's see. Let's argue with that. So I will rewrite if that is the case. Let's argue with that neighborhood. So you know that G1 is non-zero on a deleted neighborhood, and on that deleted neighborhood, let's argue with that and see. So right. So G1 has so there is a neighborhood DAR such that G1 has no zero on DAR, and in which case you take H equal to 1 by G1. In this neighborhood DAR where G1 is never zero. So H equal to 1 by G1 makes sense. And this H is holomorphic on DAR because G1 is holomorphic and G1 is not zero. So H is holomorphic on DAR and it has no zero there. It has no zero there because it's of the form 1 by G1, so it cannot have a zero. And for Z in this deleted neighborhood, Fz minus W is Hz by Z minus A power n. So Ariman, we have to argue with this D prime AR only, no? It's on this, but it doesn't matter because on the smaller neighborhood also this is true, right? So you would have got a smaller neighborhood of this, smaller deleted neighborhood. There also this argument is true. I mean, this is true throughout this, therefore on a smaller thing also. So it doesn't matter. Smaller thing is fine. So I will rewrite the slides after thinking about it after the class. So H is holomorphic on DAR, it has no zero. And for Z in D prime AR, you have Fz minus W is Hz by Z minus A power M. Now that is just coming from this. Gz equal to Z minus A power M H1Z, H equal to 1 by G1, and that is Gz by, so it is, where am I? Fz minus W you are considering, but Fz minus W is 1 by G. Fz minus W is 1 by G. And 1 by G is 1 by this, and 1 by G1 is what is called H. So that is just mechanical manipulation. It is H by Z minus A power n. Hz by Z minus A power n. Now H should have a power series expansion in DAR because H is holomorphic on DAR. So H should have a power series expansion in DAR. So let's say Bn Z minus A power n, and in which case I think you are done. B0 is non-zero because H is non-zero. H is non-zero, so B0 is non-zero, and then you are just taking Fz minus this part. Bm minus 1 by Z minus A plus Bm minus 2 by Z minus A square plus etc. B0 by Z minus A power m, and this is holomorphic on DAR. Right? What are you doing? You are taking H by Z minus A power m. So when you take H by Z minus A power m, you have got Fz minus a constant. So Fz minus all this negative part, so to say, the part where the denominator comes with Z minus A power something, that when you pull this back, the remaining is a genuine power series and therefore it's holomorphic. So this was the definition of pole. You can, subtract a principal part like this and then you get removable singularity. Holomorphic means removable singularity. And the essence of the proof is, by assuming that it is not an essential singularity, oh, we have exceeded time. By assuming that it's not essential singularity, you have constructed a G and you have two cases, either at the singularity point Ga is 0 or it is non-zero. In the non-zero case, you prove that it is removable. In the zero case, you prove that it is a pole. There was one point of confusion about, there was a little bit of confusion here. Whether it is the original disk or I am taking a slightly smaller one, let me think about it and change the slides if necessary. Maybe this is right, maybe I need to adjust it, but the proof goes through without any problem. Okay, so we will stop here.
In the last line, it should be deleted neighborhood, right?
Last slide.
For technicalities, the last line should be deleted, right?
For technicality, it should be deleted neighborhood, and then I will say that this has a removable singularity.
Yeah.
Correct, you are right. Any other question? I think some of you have another class, so let me stop recording, and those who want to ask questions can still ask.